So here, take a look at this diagram here. We have a function which is graphed, and it's a linear graph. All right. Now look at this x-axis. You've got x equals 1, x equals 2, x equals 7, whatever, and here is x equals some random number c. All right. So if you're walking along the x-axis, this is you walking along the x-axis from the left to the right, okay? And if you're walking along here, where is this graph? Is it above you or below you? Above you. And as you're walking along, in which vertical direction is the graph moving?
The right.
In which vertical direction is the graph moving as you walk that way?
Vertical.
It's so up or down?
Down.
Down. It's going down, right? So that's not a mathematically sound statement. What we could say is, as I'm approaching C, as the values approach C, Y values, are they increasing or decreasing?
Decreasing.
Y values are decreasing. Now, if somebody else is here and they're approaching C, so if you're approaching C from the right-hand side, what's happening to the Y values now?
Increasing.
They're increasing. Now, when this person gets very, very close to C, the Y values are still decreasing, and it looks like the Y value is approaching what? L, right? The Y value is approaching L. The guy on the right, when he's very, very close to C, the Y values are increasing, and it looks like they're approaching a value of what? L as well, a Y value, right? So this is where it's very, very important to differentiate between our X values and our Y values. So listen to this one more time. As we're approaching C from the left, the value, when I say the word value, that means Y. All right? So maybe we need to write that in big letters somewhere. Value means Y. Okay? Y value. As I'm approaching C from the left-hand side, the Y value is approaching L. As I'm approaching C from the right-hand side, the Y value is approaching L. Okay? So, as X approaches C from the left-hand side, can I abbreviate left-hand side from now on as LHS? Okay. Value approaches L. And then here, as X approaches C from, what's RHS? Right-hand side, value approaches L. Now, because from the left-hand side, if you look from the left-hand side, and if you look from the right-hand side, it looks like the Y values are approaching the same number L. Then we say, because these are the same, we say the limit of f of x as x approaches C is equal to L. All right? Yes?
So in this case, like the limit is more of a point rather than,
the limit is a value. Yeah, the limit is a value. Now, again, I always use the word approaches, approaches, approaches. The Y value is getting close to L. The Y value is getting close to L. And here's the question for you. Does the Y value ever hit L? No. And that part does not matter. So limit is all about what Y value we are coming close to, regardless of whether or not it actually hits that point.
Isn't that just
Okay? Okay, we're not going to confuse terms right now. It's just limits. Okay? Yeah. Different things. Different things. Right now we're just talking about limits. Okay? All right. So here we're going to estimate the limit as x approaches to -7 of 4x plus 1 using a graph, right? And so here what I'm actually going to do is I'm going to rescale my y-axis. So I'm going to go by 3s instead of 1. So I'm going to make that 30, 15, -15, and -30. Okay, so let's graph 4x plus 1 when x is, right, so we're going to graph y equals 4x plus 1. When x is 0, what's 1? What's y? 1. And then the slope is 4, right? Over 1. So that's what it looks like. So one way is you can use the graph to estimate as x approaches -7 what y value is y approaching, right? That's one thing you could do. You could just look what y value it's going to. What you could also do is use a table of values. So with your calculator, what we're going to do is figure out some of those values. So go ahead and take out your calculators and let's put some of these numbers in. So it's y equals 4x plus 1, right? So that's going to be 4 times -7.01 plus 1. And that's -27.04. All right? So go ahead and give me these values that I'm marking here. Okay, those 3 values. So go ahead and I'll give you like 30 seconds to plug those in. 0.004. And here?
Which one?
6.999. And here? Okay, so let's take a look now. This is -7, right? My limit here is 4x plus 1 as x approaches -7. Yeah. It's a little wrong because I scaled it by 3 and then I just estimated. I estimated. But what I was saying is it's not precise. So as I'm approaching -7 here, what value is y approaching? What value is y approaching? -27. As I approach -7 from the other side, what y value is this approaching? -27. So now, because from the left and from the right, okay, because these are the same, okay, I say that the limit of 4x plus 1 as x approaches -1 is -27. -7. All right. So the point is they have to approach the same value from both sides. All right. Let's move on to the next page. I have another. Because it's approaching -27 from the one side and -27 from the other side. Because it's approaching the same value of -27, then we say the limit is -27.
It doesn't matter what the function is.
What do you mean?
Like,
yeah. So from here, look, -6.9, -6.99, we're getting close to 7. Y is getting close to -27. We're getting close to 7 from the other side, and y is getting close to the same number.
Wouldn't that kind of be true, like any linear line is straight, so that both sides will be.
Yes. Anytime you've got like a basic polynomial function, there's always going to be
this
a
is
limit.
change once you get, like,
Other fancy, interesting
That's what I was-
functions.
okay.
Yeah, yeah. There isn't much to say with the boring linear
That's what I was
functions.
wondering, so I was like, well,
Yeah.
let's just be together.
Those rational functions,
Yeah.
gold mine. Yeah.
What do you think?
He was just saying that the limit is always going to exist for any linear function, and he's very, very correct. Okay, now, this is the most important thing we're going to do now. Take a look here. Take a look here. I know we've done this before, but back then, you were still, new at this. You were youngins. Now, you're sophisticated, distinguished math students, okay? So I had a student earlier from a different class entirely, different course, who was like, oh my God, like this is supposed to be the hardest thing we're doing this year, but it just seems easier than what we've been doing all year. And I was like, well, technically it's not easier, but you've learned so much that you can just handle it with better stride now. So that's where we are. So now when you listen to this now, you're gonna have like this new experience of it. So, yeah. So take a look at this. Take a look at this first picture here. And don't try to, and just follow along with me. Don't try to go ahead of me. Okay. As x approaches c from the left-hand side, what value is y approaching? L. As x approaches c from the right-hand side, what value is it approaching? L. From both sides, it's approaching L. Is that correct? So, the limit of this is L. Does it ever get to L?
No.
No. So if I were to ask you, what's f of c? There's a hole at f of c. F of c does not exist. F of c is undefined. That has no effect on the limit whatsoever. They're independent things. Okay? Now, look at this one. This is g of x. This is c, guys. Right here. This is c. What's g of c? What's the value at c? What's g of c? How much? Okay. Look, there is no graph there, but there is a point there at n. So g of c is n. It's very much defined. Now, here's the question. As I'm approaching c from the left-hand side, what y value vertically, where is the graph approaching? L. Right? As I'm approaching c, okay, if I'm here, my graph is up here. As I get closer, the graph is going down, down, down to L. Now, from the opposite side, as I'm approaching c, the graph is going up, up, up to what value? L. So, from the left-hand side, it's approaching L. From the right-hand side, it's approaching L. The limit is L, but the actual value is N. Again, the limit and the actual value have no effect on one another. And now take a look at this one. As I approach C from the left-hand side, what y value is the graph approaching? L. From the right-hand side, what y value is the graph approaching? L. Now this is h of x. What's h of c? What's the value there? L. So now here's the third example where the limit is L and the actual value is L. All right, again, that's also a possibility. So now here's the question for you. So you have three cases. You have the same limit. On the one hand, there is no value of the graph. Here, the value of the graph is different. Here, they're the same. When we did this one here, which one of those was that one like? 1, 2, or 3?
3.
3.
1.
It's like 3. Because what's the actual value at x equals negative 7?
Negative 27.
Yeah. Okay. Did somebody have a question? Okay. So, let's do this one. All right, we're going to graph this now. We're going to rely on our previous knowledge of rational functions. So I have limit as x approaches 4. I'm going to factor this numerator over x minus 4. This is limit as x approaches 4. This cancels, and I have x plus 4 left. Okay? So is that just a linear graph?
No, of course not. The graph itself is a linear graph.
It has a hole in it, right? There was a denominator here which canceled out from chapter 2. So there's a hole at what? At x equals 4. And it would be up here.
So is it a linear graph?
Okay.
It's not. You can't define it as a linear graph. Is it?
Oh, it's at 4. Sorry. All right. So, what's the limit as x approaches 4? This is x approaches 4. As I'm approaching 4 from the left-hand side, where is my graph going? 8. To 8. Okay? All right, now. Yeah. No, this is a rational function. Okay, Idan, as I approach 4 from the right-hand side, what's the y? Guys, raise your hand if you're going to answer. What's the limit here? 8. So the limit here is equal to 8. Yeah. Yes and no. No. Okay? All right. Now, numerically, if you plug these in, right? If you plug these in, I get 7.99, 7.999. Here I get 8.001, and here I get 8.01. Okay? Yes. No, you have to do it the other way, because technically the limit, yeah, that's a different function. Okay, now, does the numerical part support what we're doing over there? As I'm approaching 4 here, is the y value approaching 8? Yeah. How about from here? Is the y value approaching 8? Yeah. Okay. Plug in 4 to the actual function. What's the value? It's 0 on the bottom, so it's undefined, right? So do you see that it has a limit, but f of 4 is undefined, all right? The moral is that does not hold you back in any way, okay? All right, any questions? Okay, let's move on to one-sided limits. Okay, if you want to find the limit, the official limit of a function, you've got to check both sides, left hand, right hand. Only if they match is there a limit. Sometimes, however, the situation only calls for the limit from the right side or the limit from the left side. We call those one-sided limits. You're not comparing it against anything. It is what it is. All right? The notation for that looks like this. So this is the limit of f of x as x approaches c from the left-hand side, right? You see how it's a c minus? Where are the negative numbers? To the left or to the right? You're in the left, right? So if it's C minus, you're approaching from the negative side. That's how I say it usually. All right? So this is when you're approaching from the left side. Here, the other one is X approaches C plus, so you're approaching from the right side. Okay? Now, formally, what I was saying before, a function has a limit as X approaches C if and only if the right and left hand limits are the same and they exist, right? So it's everything I've been saying before. If from the left it's a value, if from the right it's a value, and if they're the same value, then the limit exists. Okay, let's do some examples here. Look at this. This is f of x, and I want to find the limit as x approaches 0 from the negative side. This is 0. As I approach 0 from the negative side, please raise your hand to answer this. What y value is the graph approaching? What y value is the graph approaching? 5. So that is just 5. All right? Now, as I approach 0 from the right-hand side, what y value is the graph approaching? And it's also 5. Now, this one's asking you the limit as x approaches 0. Because 0 from the minus side and 0 from the plus side, because these are the same, we say this also approaches 5.
What if they weren't the same?
Then you would say, I'm going to do one right now. Okay? Here, let's go to negative 3. Negative 3 is here. As I approach, raise your hand to answer this. As I approach negative 3 from the left-hand side, where is the graph going? Yes. 0, right? It's going up that way to 0. All right. As I approach negative 3 from the right-hand side, where is the graph going now, Gabe? 5. All right. Now, limit as x approaches negative 3, when these are not the same, we say the limit does not exist. Does not exist. Just write DNE. Not undefined, DNE. Yeah, there is.
Undefined exists, we just don't know what it is.
That's it right there. Way to go.
Why is it 5?
Okay, so as you approach negative 3 from the positive side, so if you're a little bit away from negative 3, where's the graph? Here.
Okay.
As you go closer, where is the graph going? Vertically to 5, still to 5.
Okay.
Okay? Yeah. So never ever go to that point and then try to determine it. Always see like a little bit before it, where is it and where is it heading? Okay? Some people, like in, here's a question for you. Here, what's f of 0? The limit as x approaches 0 is 5. What's f of 0? 5. Sorry, yeah. All right, now, here, the limit as x approaches negative 3 does not exist. But what's f of negative 3?
2.
How many say 5? How many say 2? Okay, so at negative 3, where is there a graph? Not here. Here there's a graph, so it's 2. So do you see that even though like it's approaching one value from the left, one value from the right, the limit doesn't exist, and the value is a completely different thing. Just to specify that they're not dependent on each other. All right? Okay, let's do some piecewise functions. Do you guys remember how to graph piecewise functions? Yes, we do. Okay, so this, okay, the partition is at x equals 1. So remember, first and foremost, you have to plug in the 1 into here. So at 1, the function to the right, or the function to the left is 3. 1, 2, 3. Okay? And this is a cubic function, right? And what do cubic functions look like? They look like this, right? So when x is 0, how much is that? 2, right? So this is going to look like this. Now, the action here is happening at x equals 1. You're looking for the limit at x equals 1. So I want to be really precise at x equals 1. I can eyeball the rest, okay? Then for the following function, I put 1 in here, and I get 3 again. Oh, shoot, that should have been an open circle before, right? That should have been an open circle before, but now it's closed, so I close it. When open and closed lie on top of each other, you just close it. And then it's a slope of positive 2. So that. So what's the limit as x approaches 1 from the left-hand side? 3. And from the right-hand side? And the limit is 3. Okay. I'm going to ruin the element of surprise for you. On your quiz and on your test, you're going to have a whole bunch of these. Without having to graph, you need to be able to figure it out. And then you might have to graph and figure it out. Okay? How do you do it without graphing? So, for the first one, this one, it's 1 from the negative side, from the left-hand side. Is that the top or the bottom?
The top.
The top. So you plug 1 in there, what do you get? 3. Then this one is 1 from the positive side, that's the bottom. You plug 1 in there, what do you get? 3. Yes, that's cool. That is so cool. You get 3 from the left, you get 3 from the right. They're approaching the same number. Does it matter if this is open or closed? No, because where they get, it doesn't matter as long as you get it from the same side. Okay? Eli mentioned continuity before. That's when that happens, but they're completely different things, so we don't want to mix the two. Okay. All right, so these I've just graphed for you. This is so exciting. I love this lesson. Okay, so these I've graphed for you, and we're just going to look, okay? It was graphed on the TI-83. It's okay. It was, it's a little bit behind the times. It's fine. Okay, as x approaches negative 2, okay. As x approaches negative 2 from the left-hand side, guys, this is negative 2. From the left-hand side, so look at what I do. A little bit before it, the graph is up here. It's going down to what value? 3. The negative values are over there. So it's coming from the negative values. It's coming from the negative side. Huh? Wait, no. You're approaching negative 2 from the side of the negative. You're approaching this number from the side of the negative. So this is a 3. Now, as I'm approaching negative 2 from the positive side, this is the important. This is where everybody gets confused. Look. Oh, I have a negative 4. Any other answers? Okay. As I approach here, a little bit before, where is the graph? Here. And then where is it heading? To negative 4. Okay? So if you like, let's draw that partition at negative 2. Well, sometimes you might not be given the function.
Oh, like just
Yeah.
like the graph.
Yeah. You should know how to do it both ways. So, look.
But then you also said you might not do that.
Right.
Oh, okay.
So, I'm approaching here, this value. So it's negative 4. So what's the limit as x approaches negative 2? DNE. Now, if yes. Now, Rachel and I were kind of sidebarring here. Sometimes you'll be given, very rarely will you be given both the graph and the function. Sometimes you'll be given just the graph, and you need to know how to do this. Sometimes you'll be given just the function, and you need to do that. So let's do this one more time with just the function, all right? Negative 2 from the minus side, plug -2 in here. What do you get?
12.
No, that's
0. Oh, 0.5? Sorry.
Oh. So it's more. That's
Okay,
what
you
I
should
I
get,
didn't see the point. My bad.
you should get 3.
Sorry.
-2 from the positive side, plug this in here, and you get -4. You see how you don't get the same value? So the limit does not exist.
Oh, wait.
Okay, here. That's the function, that's the graph. The limit as x approaches 3 from the minus side. Okay, with these, where there's clearly a vertical asymptote, okay, I suggest, because sometimes even, like especially on the test, you're just stressed and you mix up the numbers because like all the lines seem to like converge in your head. So it's at 3, right? So go to 3, 1, 2, 3, and sort of like draw a line. So you just know where you're looking at, right? Okay. 3 from the minus side, that's from the left. Okay? So go a little bit before the 3. The graph is somewhere here. And then what's happening? It's falling down, down. It's going to -infinity.
So when it's no like clear cut point, it keeps going.
It keeps going down, right? It's not.
They'll never reach it. That like. Yeah.
It's not approaching a specific value. From the right-hand side, all right, a little bit away from it, I'm here. And where am I approaching as x approaches 3? All the way up there, +infinity. -infinity from one side, +infinity from the same.
DNE.
That's DNE because they're not the same. Okay, this is an important one now. The limit as x approaches 0. Okay. From the left-hand side, where is the graph approaching? What vertical value? Huh? -infinity. From the right-hand side, where is it approaching? -infinity. Okay, here it is. Okay, now. Okay.
If those are the same, it's always going to be the same. She said that on the other thing, so it's still -infinity.
No, she's trying to explain something.
Okay, I'm trying to, okay. Because they're the same, it's -infinity. However, we don't know where -infinity is. So, when you have this situation where you have -infinity, -infinity, or positive infinity, in your answer, you write -infinity / DNE. Okay, I'm going to pause here for a minute and talk about this for a little bit. Now, here's the little, this is sort of like an off-the-record, unwritten understanding, okay? Now, when you say, okay, you can say -infinity. That's okay. All right? You can say -infinity / DNE. It's also okay. Okay, hang on. For this one, if you say DNE only for this one, not okay. Okay? Here, there is no other answer but DNE. Here, there is no other answer but DNE. Here, acceptable forms are these two. Okay? However, I'm telling you this like in general, both of those are acceptable. negative infinity or negative infinity slash dne, negative infinity parentheses dne, whatever. Now, because I want to be so careful to stress that those two can go together, I'm going to require that you write it this way. Okay? I'm just telling you that mathematically, this is also acceptable, all right? So, just putting that out there. But myself, personally, I'm going to require this one, okay? Yes, or on a quiz. Okay, so, take a look at this one. The limit as x approaches 0, sine of 1 over x. Guys, look at this. It's the limit as x approaches 0. Notice this. It's going from like negative 1 to 1. So if this is 0.75, then here this is 0.25 and negative 0.25. And look at what it's doing. It's oscillating like crazy, right? In the middle there. So we have no idea what's happening. You know what? Let's zoom in. Oh, that made a lot of difference. Okay? So, as I approach 0 from the left-hand side, and as I approach 0 from the right-hand side, where is it going? Do I know that it's here or here or here or here? Do I know in what part of the oscillation it is?
We have to plug it in.
No.
So you have to put
Okay.
the limits above.
No.
Okay, hang on. So, the plugging in option, does the limit have anything to do with the actual value? No, we're not going to, no, we can't. Because it's going to approach infinity. It's 1 over x. How can we plug in a number very close to 0? It'll give us a very large number. Okay, so it's, okay. Because you don't quite know what's happening, we say DNE, DNE, DNE. The point is, the reason is, if you put in, guys, if you put in a number close to 0, 1 over 0.00000, whatever, this is going to be sine of like 12 trillion, right? And what's sine of 12 trillion? I don't know. Once it gets there, I still don't know. Like sine is oscillating. And when I get there, how do I know where it is? So it's infinity. Okay, now, this is important here. Why a limit at a point might not exist? Okay, what are the situations? 1, okay, so the limit will not exist, or it's DNE, if, so the first case is if f of x approaches different values from the left and right. So of these, which one qualifies? A, B, C, D, or E? Which one? Different values from left and right. Huh? B is a good one. Okay, B. Second case, if f of x increases or decreases without bound. So if f of x goes to positive infinity or negative infinity. So which one of these will qualify for that? C or D? Or, so this is an actual class of its own. If f of x oscillates between two fixed values, so like E. Okay, and the very, very last thing. So far, I've always been saying as x approaches 0, as x approaches 3, as x approaches 5. Now, let's get away from that. Let's talk about end behavior. What happens to this as x approaches positive infinity? If I get on my spaceship and I go to positive infinity, keeping my eye on the graph, what y value is that approaching? Negative 3. What if when I'm approaching negative infinity? Negative 3. And with this, because we're not approaching the same point, okay, we're going to negative infinities, there is no left and right limit here, right? That's only if we were approaching a point. Okay, here. The limit of sine of x as x approaches infinity. So I go there. Where is it? Is it at 1? Is it at 0.1? Is it at negative 0.1? Do I know? I don't know. So it's DNE.
It's oscillating.
Because it's oscillating between 2 points. Because how do I know where infinity is in order for me to get there, in order for me to check? No, because here it was... Okay, this is this function. I'll talk about that in a minute. As x approaches infinity, here, what's happening? What do we think? Yeah. It's oscillating, so it's DNE. And as I approach negative infinity, 0. Now, let me talk about this function for a minute. Oh, no, I'm so sorry. Okay. Huh? Okay. As I approach infinity, look at what's happening to the function. It just keeps oscillating, so it does not exist. But as I approach negative infinity, it gets closer to it. Okay. Let me talk about one thing here. So this is a function that looks like this, e to the x. E to the x sine 3 pi x. So we know what sine does, it oscillates. And we know what this does, e to the x, right? So, okay. So sine of x looks like this, right? E to the x looks like this. Okay? Now, when you combine these, right? Here, e to the x goes to 0. So whatever function it combines with must go to 0. So do you see how this is the married version of e to the x and sine of x? So when you're playing like any string instrument, let's say, right? When you're playing or like the guitar or the violin or whatever, or when you're playing even like the drums, all right? And you hit the drum and it's vibrating. And then what happens as you gently put your hand on it? Eventually it stops if you gently put. Why? What do we call that? We call it a damping, right? It dampens the oscillation. It dampens the frequency, huh? That's the damper pedal in the piano. These types of functions are called damping functions. All right? This is how you draw that frequency. Okay? All right. So this is going to be your homework for